So, similar to calculating our enthalpy change, okay, it's the same overall process. If we go through and look at the equation we've got, okay, for a change, you're going to see a delta. The S is now our symbol for entropy. What's that 0 mean? Okay, that would typically mean degrees, but in our language here, what it's going to refer to is a standard. Okay, the next symbol we see is this goofy looking E, which is a capital Greek E. If you see me draw it, I'll usually draw it out like that. That represents sum. So what you're now going through and doing is everything that comes after that, you're going to add all together. Okay, so that's our sum. The next thing that pops up is the letter N, which is already coded on this, but the N is the coefficient from the balanced chemical reaction. So I'm not going to write that one out, but I do want a quick example here, because some people struggled with dealing with that. Let's process. It's the only equation I have off the top of my head. Okay, what is N in this first term? It's 1, okay? And we're going to come back to that 1.5 because it's an important statement that I think people are misunderstanding. Okay, it's not going to be 1.5 because we've got to look for the products. That's what that parenthetical is referencing. I'm looking at the standard entropies, okay, for my products. So that thing in orange is one thing. That's one piece of information. Okay, that's one variable. So that's where I would go to my table of entropies, and I'd pull data out of that. Okay, the N is corresponding to the coefficient on whatever thing I pulled out of the table. So for this particular scenario, what I would go through and do is I would go into my table and I would pull the entropy, or find my entropy for water. Okay, so there's my S value for water, and I want to multiply it by the coefficient for that thing. What is the coefficient? 1. Okay. If we go through and now look at the other side, what's happening on the other side? We're going to repeat our process. We've got our sum again. We have our N, and we now have that S for our reactants again. What is the N now? Okay. And this is where the challenge comes in. When we're going to our table, okay, for our entropies, what we're looking for is a single species. Okay? So when I'm going into the table, I'm not going to find a single species. I'm going to find 2 species. One of them is H2. One of them is O2. Okay? I have to add those 2 terms together. That's the sum. So what's the coefficient that I'm going to be using? Insanely misleading phrasing of that question. It's not a single coefficient. It's 2. The coefficient that I would use for looking up the entropy for my hydrogen would be 1. The coefficient that I would look up for my oxygen would be 0.5. Okay? I personally would go through and do it kind of as it's shown here, and we move to an example, I'll show it in a little bit more detail. Okay? And then I would process the last part of the equation. Okay, well, actually, not even that. I would take the sum for this side. So I have the sum of my reactants. I would take the sum for my products. That was that goofy looking E. Once I have those sums, now I would complete the last step. What's the last step? That's recognizing that I need to do a subtraction. And I'm going to take that orange thing, whatever that number was, and I'm going to subtract the purple thing, whatever that was. Kind of, sort of? Okay. Some people are going, yeah. Some people are going, I don't know what you just colored over. What I tried to color over was all the same stuff. Okay? So let's look at a situation where we have actual numbers. calculate the enthalpy change, or entropy change, sorry, for this reaction. Okay? Does it match our prediction? So first and foremost, let's take a hot second to pause. We don't want to do any calculations yet. We actually want to make sure we understand what's going on. Does this match our prediction? What are we talking about when it matches our prediction? Sure hope you guys aren't writing any numbers down. Knock it off. What's our prediction? What are we trying to predict?
Positive or negative.
The entropy change. Do we predict the entropy for this reaction to go up or down? Okay. Why do we think it should go up? Combustion is talking about endo and exothermic. I doubt you have entropy tied to a chemical reaction type.
There's two gases on the product and only one, like the coefficient.
The first thing that we would go through and do is look at our species. Okay? I would start with the phases because we see a huge entropy difference between solids, liquids, and gases. And in particular, our gases have massive amounts of entropy because they have constant movement everywhere. So if I'm looking at my entropy, that one I can ignore on the reactant side. On the product side, what can I look for?
Can't you look at both of the gases?
I have two gases. So I'm going from one gas to now two gases. That would suggest, okay, ignoring anything else, that our entropy should go up. Because we now have more species. And they're all gases. Kind of, sort of. What else should we look for?
Coefficients.
The coefficient. This is 13 gas molecules on the reactant side, and it's 8 and 10 gas molecules on the product side. So not only do I get more different types of gases, I also get a larger number of them. Both of those things contribute to the entropy of the products being larger than the entropy of the reactants. And if that's the case, when I go through and calculate my delta entropy, if my product value is larger, I don't know, what's a big number? 500. Okay, what's a small number? 250. Really? I mean, it works, but okay. You're just picking random numbers to help you get an idea of this. 500 is a larger number than 250. What would be the sign for my delta S? Positive. I'm using those numbers to help me get to the sign. That's it. Okay? So for our prediction, we would expect the entropy to go up. We should get a positive value when we run our calculation. Okay? How big of a positive value? Do you think really big, really small? If it's small, we're saying the entropies are relatively close to the same on the reactant and product. Did we establish that? No. If anything, we said the product has a whole hell of a lot more entropy, which means that delta entropy value, whatever number we calculate, should be a big value. What is big?
Thousands.
Yeah, and that look of like, I don't know, is a good look. Okay? Until you have experience with running calculations, you don't necessarily know what's big. Okay? So that's where your experience in doing homework and practice would help with that, to give you an idea of a scale on what's big versus small. Kind of, sort of? So we've got a solid prediction now. We think we should get a positive value. So with all of that, we can now erase all of that stuff. We've got our numbers up there, and you can now start punching in to your calculator with how to go through and solve this particular equation. If you've got questions, raise your hand. I'll come to 0.8 joules per mole times Kelvin, right? Mm-hmm. But it's not just the sum of the products minus the sum of the reactants. It's account for all of those species. That's that N value. It's the coefficient. So what was the coefficient on my CO2? 8. So what I need to do is make sure that I drop that coefficient on my CO2. Okay? What was my coefficient on the water? I have to drop that coefficient on my water. Okay? Then go through and do my subtraction for the next part, and I go through and look at my reactants. What are my reactants? C4H10, so 231.0 joules per mole Kelvin, right? Coefficient, we'll jump straight into it,
2.
is a 2. We're going to drop that plus there, plus there. And then for our oxygen was 205.0 joules per mole times Kelvin. And again, I need my coefficient. I've run out of colors. 13. Now it's just a question of entering it all into the calculator and getting it right. Sort of. Okay? More often than not, what's going to end up happening is you will take your 8 times 200, so what, 1,600 ballpark? Your 10 times 200, 2,000. Okay, so 1,600, whoops, plus 2,000. Should do this work down below. Plus our 2,000. 2 times 200 is about 400. I'm lost there. Help me out. 13 times 2? What?
26 minutes.
I shouldn't have been lost there. Thank you for that. 2,600, and I'll add that up. Okay. And I'll get 2,000 plus 1,600 is 3,600. Okay. And I'll get 3,000. Okay. Then I run my subtraction. Okay. When I run that subtraction now, what's my answer?
Positive 4 or 600.
Okay. Based off of my cruddy work, it might be positive 600. Are you getting positive 400 as the actual? Okay. So my estimate comes out as a positive 600. Okay. If you use the actual numbers, give me a number again. 4,000.
470. Oh, the actual
400.
was 3,598 minus 3,127.
Yeah, which gave you 471. Okay. So if you're running the actual calculations, you should be getting positive 471. Okay. I wouldn't be surprised if a few of you running this calculation got 3, 2. Come on, Mike, do math. 32 minus 400. 36 minus 200. Is 32 got ballpark 6,200?
Oh, I see what you did.
Okay. Did anybody want to volunteer that they got a number in the ballpark range of that? Okay, and that's fine. What happened? This minus sign has to be distributed through the entire reactant side. So if you're just writing this out according to your numbers and are running this calculation not very carefully, what you will end up doing is adding this term to the overall term. Everybody see that? That's PEMDAS, whatever it is. Okay? So make sure that you're careful to include that minus sign either distributed through your calculation or you run the products first, then the reactants, then you run your subtraction. Does that make sense? Mm-hmm. Everybody on board? Okay. Questions about it?
I don't know, I got a whole completely different number.
If you're getting a whole completely different number that isn't in the ballpark of that 400, you're probably made that subtraction wrong. You're doing the exact thing that I'm telling you to watch out for, which is what your work shows. Your work shows that you didn't distribute that minus sign. Okay? So we've got a positive 471. Okay? Is that a big change or a small change? Can I erase all the work? Because it's creeping me out. It looks ugly. Okay? We got an entropy change of positive 471. Okay, what are the units on that?
Joules over moles times Kelvin.
Is it per mole?
Wait, no.
We actually canceled the moles in each of those individual calculations. That's what that coefficient did. It's just going to be joules per Kelvin. Okay? Is that a big number? Well, look at the entropies for each of the individual species. Is 471 larger than each of the individual ones?
Yeah.
Yeah. So that could lend credence to the fact that it is a larger value. Does that make sense? Right? Units on this were joules per Kelvin, right? We've got our joules. Is this a large number in the grand scheme of enthalpy? What were the units on enthalpy? Kilojoules. Is this a large number? No, the entropy contribution is generally small, which is why, to a first approximation, we can get away with referencing bond enthalpies and ignoring entropy. Which is why the scientist that discovered entropy was like, stop it. It does have some value. We have to incorporate this in our calculations. That's why we're missing some explanations. Okay? So relatively, the entropy term is smaller than the enthalpy term. Okay? But it does have value, and in certain circumstances, it can overcome the enthalpy. Kind of, sort of? Okay. So, I meant to talk through all that. Oh well. If we go back and look at those reactions that we talked to, we have the combustion of our butane, right? And we calculated the delta H. The delta H we got was negative, right? We also calculated that the delta S increased. We had a positive value. When we go through and looked at the other one, so this is review stuff back. If you go back and look at your notes, this is what we noted. The production of cement, it was an endothermic process. Okay? We got a value that was positive. The entropy also increased. Okay? So those are just summaries of the calculations we've run, both on Monday and now today. Kind of, sorta? Okay. Which takes us to this slide, which is not appropriately written yet. So ignore most of the text, but look at the blue box. Talk at your table, figure out what you think's going on in the blue box. In this reaction, the products are less energetically stable than the reactants. Why is the reaction able to happen anyway? So what do we got? Why was this reaction able to happen anyway? I can think of a couple answers. Why do we think this reaction happened anyway? We're looking at an apparent endothermic reaction. How can I get it to happen?
Well, I don't know, this is like way off a bit, but don't reactions like to be stabilized or like stable? So
Yeah. Are the products more stable than the reactants?
yeah.
Are the products more stable than the reactants?
Oh wait, no.
It's an endothermic reaction. By definition, your products are less stable than your reactants. Why does it happen? Yeah, it will have to absorb heat, but why is it naturally going to do this? As a hint, stop looking at the enthalpy. What else should you consider? The entropy. In this particular scenario, the entropy is overcoming the barrier produced by the enthalpy. And that drastic increase in entropy, we're going from solids with effectively zero entropy to now a gas with tons of entropy, is able to overcome that energy difference for our enthalpy, the bonds breaking and making. This is one of those scenarios where our entropy contributes wickedly to the overall system. Okay? That's the answer we should be going for. The other way could be, I just put a bunch of energy into it. Okay, how'd you put a bunch of energy into it? How do we get energy added to any reaction?
Heat.
You just added heat. You just heated it up. Okay, so how could you prevent this reaction from happening? Cool it down. Remove all of that heat. What is that heat contributing to? the motion of particles. That heat has a direct effect with the entropy in the same direction. So if I cool this reaction down, the entropy effect now becomes less strong or less dominant. And now the reaction is dictated solely based off of the enthalpy. Well, the enthalpy says it doesn't happen. Okay? So what does that mean for us? We're going to have to come up with a way to tie enthalpy and entropy and temperature all together to represent a larger energy term. Okay? So things tend naturally to go from lower entropy to higher entropy. Okay? This is just kind of how things happen. Okay? We don't expect these orange and black balls to evenly disperse where, that's the wrong word, where all of the black balls go only to the left and all of the orange balls go only to the right. What we would expect is that for them to eventually reach a state where they're all evenly mixed. Okay? It would be really shocking to mix these things and then to freeze the system and be like, oh my God, all of them are on one side and all of them are on the other side. Like, how did that happen? Because that's really weird. The probability for that to happen is really, really challenging when we consider how all those things navigate. So when we talk through, and this is something we see, okay, if you add cream to your coffee, you shouldn't, because cream is nasty. It destroys the flavor of the coffee. Okay? And if you're like, no, it doesn't, you've had bad coffee. Fix that problem and everything gets better. Okay? When you add the milk in, what happens? It swirls and disperses through the whole system. Okay? Particularly if you give it enough time to do so. It's naturally going to mix. Okay? That's a matter of entropy. Okay? They will move around and they will spread out. The real challenge is that once I've poured it in there, would I ever expect it to unmix on its own? No. Why not? That's going to more order or less motion. We're taking all of that milk and we're putting, or cream, whatever you want to call it, and putting it into one space versus the whole container. Those things move, and as they move, we can't revert back to that unmixed state. And this is going to introduce a fun little word called spontaneous. Okay? Spontaneous is the natural tendency for things to do something for us. Okay? It says nothing about time, okay, which is an interesting dilemma. So, second law of thermodynamics is really addressing this. Okay, we now define spontaneous as something that results in an increase in entropy for the universe. Okay? These are weird expressions that really ultimately just say our entropy is constantly being positive. We look at the universe, it's always going to go up. Okay? Can I make a system where the entropy goes down? Yeah, but the only way I can make the entropy of the system to go down is if I make the surrounding entropy go up. You can spend all the time you want in the system, your bedroom, keeping it clean. But if you're spending all that time keeping that clean, what happens to the rest of the house?
It's dirty.
It gets worse. Okay? That's what we're sort of referencing. Okay? So we got another blue box. Does the entropy of the surroundings increase or decrease in an exothermic reaction? What about an I think I said them backwards. Exothermic reaction, what about an endothermic reaction? Talk at your tables and try and figure it out. Let's look at the exo. What happens to our energy? What happens to the enthalpy? We're looking at that term. Where's all that heat energy going? To the surroundings. Which means your surroundings absorb that heat and do what? They have more motion. And more motion means entropy increase. what's happening with that endothermic reaction? We're now looking at the flip. That energy is going into the system, which means our surroundings have lost that energy, or temperature is effectively dropping, which means the entropy of the surroundings drops. Okay? And if you're trying to figure out, like, how does that all work, yeah, it's challenging to manipulate that, and it usually takes a little bit of time, in my opinion, to process through it, and in my opinion, also go very, very, very slowly. Okay? And what we're addressing is this expression kind of right here. The entropy of your surroundings will be equal to the negative of your enthalpy divided by the temperature. Okay? So we're looking at how the temperature affects this system and how it's tied back to our enthalpy. This goes all to our surroundings, not to the entropy of our systems. This is only talking about what's happening with our surroundings. Okay? So we can encounter a couple scenarios. Okay? Before we get into these scenarios, a question was brought up that is really, really important. Okay? And it is addressed technically in one of these boxes. Okay? So let's double back to that slide where the question popped up. The question, is here. An exothermic produces more energy, stable, and delta S was positive. This statement is not saying exothermic always means entropy increases. It doesn't say that. What it says is for this chemical reaction, it was an exothermic reaction and entropy increased. So it is specific to the chemical reaction. Okay? Why does that become important? Well, that's now what we're looking at within that next slide. We're talking about an exothermic reaction. Good grief. An exothermic reaction where our entropy increased. So the example that we looked at, I believe that was our combustion reaction, is sitting in that quadrant. Okay? Could we have a reaction occur where it was exothermic and the entropy for our reaction decreased? We can. That's a different possibility. Kind of, sort of? Okay? So what we're trying to figure out, losing power on all my devices. It's even better, making squirrel noises I'm finding nuts. Okay? If we're going to talk through our spontaneity, what do we want for our spontaneity? If we talked about our enthalpy, when did we have a spontaneous reaction? What happened with our enthalpy? So I'll draw reactants arbitrarily. Where should I draw the products for a spontaneous reaction? And this becomes hard because you start to get thinking about the kinetics, the speed at which it happens. I don't care about the speed. Which is better? Which is more spontaneous? Having a ball, let's make a ball for our reactant, which is more spontaneous? That ball going up in energy or that ball going down in energy? Down in energy. You take a ball, when I let go of it, does it go up? No, it goes down. Okay? So seeing things naturally trend to a lower energy state is a more spontaneous process. Again, we aren't saying nothing about the speed at which it happens. We're just saying that that is a favorable system to do. You should be charging. Why are you going black on me? Okay? Now we'll delete our energy diagram. That was not what I meant to do, but whatever. For entropy, what entropy do I want for a spontaneous reaction? Second law of thermodynamics. I need my entropy to go up. So I would need a positive entropy. What was my delta H? Sorry, we said the products were lower than the reactants. So what does that mean about my enthalpy? Say again. Negative. The products are lower in energy than my reactants. When I take products minus reactants, that's going to get me a negative value. So if I have a negative system, that would suggest it's spontaneous. But what did we say about the entropy? When is the entropy spontaneous? When it's positive, when my entropy increases, or when my entropy decreases? What is the natural state for entropy to do? Increase. Everything moves to more motion, more disorder, which means when I look for spontaneity evaluating the S, I want to see my delta S be positive. That says spontaneous, whatever that word is. What about the other one? Because here it's negative. Well, if positive is spontaneous, what's negative? Not spontaneous, okay. What goes with our other system? Delta positive a positive delta H would be not spontaneous. A delta S that's positive would be spontaneous. What do we notice?
The negative positive, so that would make it.
Okay. Which of these systems would we expect to be spontaneous? Which quadrant is spontaneous with enthalpy and entropy? Top left. This is the only one that we would expect to be spontaneous. Okay. How about the lower right? No, it should never be spontaneous. Does that mean it can't happen? No. What do we have to do? We have to put in a crap ton of energy to force that reaction to happen. That's expensive. So if we're going to try and target different chemical reactions on what we're trying to go through and do, we're hoping for a system that does not hit that lower right quadrant. How about the upper right? Would it ever be spontaneous? What do we say was the relative size of the terms? Delta H had what units? Try again, delta H. Kilojoules. What was delta S? Joules. So I could look at a non-spontaneous delta S that's a small value, and I could look at a spontaneous delta H that's very, very large. Which one dominates our interpretation? The enthalpy. So now it becomes spontaneous. So we have to be able to look at effectively the two starred boxes and look at how we can manipulate the system to change the value or the weight of our entropy and our enthalpy relative to each other. Okay? What does this mean we go through and do? We're now going to have to actually quantify and come up with a relationship that defines all of these individual pieces. So what do we get? We introduce a new concept. I believe it's new. Right? We get Gibbs free energy. So you had enthalpy discussed. And we go, oh yeah, bond energy is super important. Then you had entropy get discussed. Oh, entropy is also this equally important thing. Somebody else came along and said, okay, look, you're both important. We need it in one expression. How do we tie those two concepts, because they're both addressing energy, into a single unified theory? Who did that? Gibbs, which is why we refer to things as Gibbs free energy. What did Gibbs go through and note? A couple big equations come out of this, looking at the relationship with our overall energy for our system relative to delta S. So when we're looking at these blue boxes, those blue boxes are ultimately coming about because he looked at systems where we did not have an enthalpy change. So enthalpy... Okay, I'm going to have to hold on to this. Okay? So delta G, delta H, minus T, delta S. Okay? When we went through and wrote this out, I believe we did it in colors, right? We said this one was spontaneous, non-spontaneous. Right? Everybody remembering that? These were our crude notes that we put on the other side. Earlier we talked about the positive. We said positive was spontaneous. The negative we said was non-spontaneous. Positive is still a spontaneous system. And the other one is non-spontaneous. How does this check out? Okay, well, if we're considering our delta G system, okay, a negative delta H means when I run the calculation, we'll look at the upper right quadrant. That's not my right. Your upper right? No. Left. Upper left quadrant. Okay. The delta H was negative. Minus a temperature. I don't know what the temperature is. But what sign will the temperature have? Will it be positive and negative? Because I got negative temperatures, don't I?
Yeah.
What were the units on our entropy? Joules per mole Kelvin. Which means what's the sign on my temperature? It will always be positive. And then I look at my delta S. For that upper right-hand quadrant, my delta S would be a positive value. I go through and run this calculation. I'm going to get a negative minus a positive. What happens to my value? Will it be negative or positive? A negative minus a positive. It's going to be negative. When is it going to be negative? Always. There is no temperature value I can plug into the system to change the sign of delta G. Which means when we're talking about delta G, guess what? A negative delta G is spontaneous. What happens when we look at, which quadrant do you want to look at? Take a pick. Too slow. Lower right-hand corner. What was our delta H for our lower right-hand corner? A positive. Minus our T, what was our delta S? A negative. Okay? I've warned you that that negative sign is going to be a pain in your ass. What's a negative times a negative? What's going to happen? It's always going to be a positive G. It doesn't matter what temperature I put in, I'm always going to get a positive G. That's a non-spontaneous system. When? Always. What happens with the upper right-hand quadrant? What's our delta H? A negative value. Minus, what's our delta S? Ooh, what happens when I do the negative times the negative? That becomes a positive. Will this always be negative? Will it always be positive? What's going to change it? The size of the temperature. A larger temperature value means that when I run that calculation, this can overwhelm the enthalpy. It can overwhelm the other term in our calculation. So that reaction now becomes very heavily temperature dependent. And I would have to run the calculation to verify the magnitude of those systems. Kind of, sort of? Right? We did 3 out of the 4. Guess what you should do on your own? Yeah, you should go through and do the lower left-hand corner. Is that something we should talk through together, or should we move on? Move on. I like that idea too. Okay? So, if we go through and look at the production of cement, okay, what did we say? What were our terms that came out of this? So this is pulling up our notes. Okay? I know you have great notes on it because you wrote it down. What was your delta H for the production of cement? Yeah. You asked the question about all of that, so your notes are fantastic on
For the
it.
production of cement, it's a positive delta H.
It's a positive delta H. What was your delta S?
Positive.
Why can I get this reaction to run? Okay, if I'm looking at a positive delta H and a positive, how did I get this reaction to run? We answered it early on. How did I force it to happen? I had to put tons of energy in. You mean I had to increase the temperature? There it is. It comes out of looking at that expression. That's the beauty of the Gibbs equation. Yeah? You're not as excited as I am. Be more excited. That could be dangerous. Okay? So calculating our Gibbs free energy. What's going to happen with this? You're going to have all sorts of fun now having to deal with calculating our Gibbs, which means we need this expression, delta G, delta H minus T, delta S. Remember that minus sign is a pain in your butt? You need to pay attention to it. Okay? If you're one of those people like me that loses minus signs right and left, that's probably something that if I was given the opportunity to write down a cheat sheet, I would put that on my cheat sheet so that I did not forget that that was there. Okay? So that I can now manipulate it. So if I'm now given a question where I have to calculate the delta G for the reaction at a particular temperature and at another temperature, I can now go through and ask or answer, is it spontaneous or not at each of those individual temperatures? And don't stop recording. Walked away from it again. Kinda, sorta? Do you think you guys can do it on your own? It should theoretically just be a plug and chug. Everybody loves those, right? Our delta G, what was our delta H? It's a positive 178.3 kilojoules per mole, right? I'm going to put that in parentheses for my sake. Minus my T, what's my T? 298. Why not 25? I have to make sure I take into consideration that temperature conversion. Okay? Hooray! And if you don't remember that temperature conversion, that's also okay. Write it down. Put it down. What's our conversion? Kelvin is 273 plus our degrees Celsius. I heard a couple people happen to memorize also that's 273.15. Good for you too. I don't know why I have that number down either. Okay? So cool. Now you won't ever have to remember that because that's on your cheat sheet. That's on that list that I said you should be writing stuff down that you need to have memorized so that when it comes to the quiz, you're ready to go. What's the next thing we put into our equation? Our entropy. 160.2 joules mole Kelvin. What happens? The Kelvin unit cancels, and I get joules per mole. I could go through and run the subtraction. Right? I have 178.3 minus, trying to not look like an idiot. I give up. What's 298 times 160? A large.
139.
Say again, 3,000?
47,000.
47,000, okay.
739.6.
7,000. All right, I can't do my math. 796.
36.
36. If you needed more evidence why I don't teach 151 or 152, it's because I don't know what it is. I don't do with numbers well. Okay, so cool. We run this calculation. What are we going to get? We're going to get a negative value, which would say the reaction is spontaneous. Except didn't we say it's not spontaneous?
Do we need to take into account the conversion of kilojoules to joules?
You tell me, can I subtract two different numbers with different units?
No.
Do I need to take into account the consideration of the units?
Yeah.
Yeah. This was in joules. To make it into kilojoules, I'm going to have to drop my decimal point in there. Okay. Now 178 minus 47, and I'm going to get a positive value, a non-spontaneous reaction. And since it's non-spontaneous, I'm not making cement at 25 degrees Celsius. I'm a little nervous that this is cement or concrete. Based on the formulas, I'm going to say they're trying to make concrete, but could be wrong. Okay? So we can't. I changed the temperature. Instead of running it at 25 degrees Celsius, I increased the heat to 1,450 degrees Celsius. Now what I do, I plug in my new numbers. Do I plug in 1,450? No, plus 273. Also take into consideration my joule to kilojoule conversion. And when I run that calculation, what am I going to get for my delta G? A negative number, and that's all I really cared about in this particular scenario. The rest of it is just you punching a calculator. Make sense? Cool. What is the minimum temperature required? So in this case, we picked two random values. We picked a low number, 25. Why not? Room temperature seems low, and then absurdly hot. Okay. What is the minimum temperature necessary for this reaction to occur? Ooh. How do I figure that out? What sign does my delta G need to be? For it to be spontaneous, what sign does my delta G need to be? It needs to be negative. Negative what?
Anything.
Negative anything. So does negative 1 work? Yeah, so I could plug that in. I say my delta G is negative 1. I know my delta H. I know my delta S. What do I solve for? T. Lovely. Does negative 0.9 work? Yes. Am I going to get a different temperature? Okay, so we'll talk through it again, because why not? Okay? That minimum value is going to happen at the transition point for my delta G. If my delta G is less than 0, it's spontaneous. Did I do that right? That's less than 0. Yeah. Okay? If it was greater than 0, it's non-spontaneous. So I need any kind of negative value. Are you making fun of my handwriting? You are. Thanks. Screw off. I'll erase it then. Okay? So my transition point between that positive and that negative is my delta G equals 0. That's the value I need to know. So I can now go through and say, well, my delta G equals 0, which equals delta H minus T delta S, because we've spent some time now, like all of 10 minutes. You've got that memorized now. Delta H is 178.3 kilojoules per mole. Positive or negative?
Positive.
How do you know it's positive? Okay. Some people are like, it says it's positive. Sort of. I would argue it implies it's positive. Okay. For me personally, I would like to include parentheses with a sign on it. Why? It calls attention for me personally so that I know what I'm looking at. Do you feel you need that extra information? Then make sure you include that sign. If you don't, then don't worry about it. And because we were making fun of my handwriting already, I should fix that. 178.3 kilojoules minus T. I don't know the temperature. That's my unknown. What's my delta S? Okay, cool. Another positive 162.2 kilojoules per mole times Kelvin. What can I now do? We will eventually have to convert at some point, so deciding when you want to do that is up to you. Okay? At this stage in the game, you theoretically have done these kind of conversions so much that you're able to make that conversion by just shifting your decimal point. That's also one that I've screwed up so many times in my life that I try to not just shift the decimal point. Okay? But that again comes back to your success within it. Once I've got my conversion set up, I can now do the algebra to solve for the temperature. What do I get for the temperature? Did anybody actually do it?
1,114.
Yeah, cool, I did it right. That makes me feel better. 1,114 Kelvin. How do you know you should be solving for it in Kelvin and not degrees Celsius?
That's what we get. It's in Kelvin.
Cancel out the other Kelvin to the units.
Okay, so you had lovely answers. You're going through and saying, well, it's in units of Kelvin in my calculation, so I should solve for it in Kelvin. What if the question said degrees Celsius?
Then change it to Celsius.
Okay, so your question should be clear. What if the question's not clear?
Kelvin.
Why Kelvin and not degrees Celsius?
You're not gonna say no. It's just like.
Why do more work if you aren't forced to? Stop where you have a representation for the answer. And if someone wants a different unit and they didn't tell you they wanted a different unit and they take points off, what do? You come back with the exam and say, tell me where it says this unit. And if it doesn't, that's when they should bend and they should give you the points back. They don't always, but what happens if they don't then? Yeah, jump the ladder. Okay, move to the next person up the tree. That still doesn't guarantee you're going to get your points back. Okay, because ultimately someone higher up the ladder is going to be like, you're fighting over 1 point. No. Does that make sense? Shouldn't have told you that since I'm the one responsible for your exams right now. Okay, we good with it? Cool. Pretty slides. So the reaction-produced cement must be done at very high temperatures. Okay, so when we're talking about all the cement and concrete that we deal with in the world, okay, to go through and produce it takes an insane amount of energy. And if it takes an insane amount of energy, what does that mean to the cost? It goes up a lot. Okay? So one of the things that we might consider is if you look at our roads, do you see concrete everywhere? No, you see asphalt. Why do you see asphalt everywhere and not concrete? It's cheaper. Okay? So it's that cost differential that's causing different materials to be used. Okay? Asphalt's also cheaper because of all the subsidies, because it's petroleum-based and different system. Okay? In any case, we're producing this concrete. That takes lots of energy. To get that energy, we're usually burning fossil fuels, and in the process of burning fossil fuels, we're producing more carbon dioxide, and we get more greenhouse gases, and it makes things even worse. Okay? So we want to be cognizant of those loads behind those systems. What does that ultimately mean for us? Our really active area of research is how do you make concrete with less energy? Okay? Because if it takes less energy, they can make it faster, cheaper, better, okay? And they can start to change those systems. Make sense? Okay. Remember how I said there was no way in hell I was going to get to where I wanted to get? Jiminy Christmas. Supposed to make it 39? Gotta be kidding. is what it is. This is where we'll end it. Okay? Place each reaction or process into the correct box and explain why. Okay? We still officially, nope, never mind, that clock's slow. This is where we'll pick up class on Monday, thank you. And I'll talk, try again, yeah. Monday's a holiday. This is where we'll pick up class on Wednesday. Okay?